Hey everybody, it's Mr. N here, and we are going to do the 2-4 lesson right now. So this lesson is on the exact definition of a limit. Now I know we've defined a limit and we've given what a limit is and we've talked about it, but this is the actual true definition. What we've talked about has been a quick way of defining it, but here's what it really is. Now, for a limit, we said as it approaches. Remember, we wanted to take values near A but not at A. And so that was what we were saying. But how do we know how close? 0.01, 0.001, 0.00001, etc. So that tells us that we can define how close by coming up with the definition of a limit. So let f be some function defined at every number in some open interval containing a, except possibly at a itself. So we've got this function on this open interval, and now we can say then the limit of f of x as x approaches a is L. The limit as x approaches a of f of x is L if for every number epsilon greater than 0 there is a number delta greater than 0 such that the absolute value of x minus a is between 0 and delta. Then the absolute value of f of x minus epsilon will be f of x minus L will be less than epsilon. So in words, we're saying the function values f of x approach a limit L as x approaches a number a if the absolute value of the difference between f of x and L can be made as small as we please. Let's fix this. Can be made as small as we please by taking x sufficiently near a but not equal to a. Okay, so here's what it's saying graphically. Let's take a look at this. Based on this curve, if I have this distance delta that I'm from a, whether I go in this direction or this direction, it's not going to give me these equal distances epsilon. Does that make sense? Because the curve varies. So this distance here and this a plus delta will be different than the L minus epsilon, but we need to find it to be somewhat consistent. And again, we need to take a look at the definition doesn't mention f of x when x equals a. The function f does have to be defined in order for the limit as x approaches a of f of x to exist. Also, if f is defined at a, then the limit as x approaches a of f of x may exist without having the same value at f of a. So we've already talked about this situation where the value at f of a can be different than the limit. But again, as we get closer this way, we're going to get closer this way from epsilon to L. Okay, but it can vary. So because it can vary, we need to always find a delta that's going to be as close as possible to A. We're going to end up with possibly two deltas, but you want the one that's going to be as close to A as possible. So now let's take a look at what we have here. We've got one-sided limits. The definition of a left-hand limit follows suit, and then we can say the limit as x approaches a from the left of f of x if for every number epsilon greater than 0 there is a number delta such that if a minus delta less than x less than a, then f of x minus L is less than epsilon. Right-hand limit as x approaches a from the right, f of x for every number epsilon greater than 0. So we're trying to get that epsilon to be as small as possible, and the only way to do that is to get the delta to be as close as possible. So there is a number delta greater than 0 such that if x is between a and a plus delta, then the limit, or f of x minus the limit, is less than epsilon. So the left hand and the right hand follow suit with up above, and then the theorem x minus a of f of x equals L if and only if the left and the right both exist and both are L. So the limit exists if the left and the right are the same, and we've talked about that many times. So looking over here is what we have on some example problems. Let's go ahead and find these limits. So on this one, we're asked to sketch a graph. So I'm going to sketch the graph right over here on the side. And I've got this upside down parabola, 4 minus x squared, if x is greater than or equal to 1. So at 1, I'm going to get a value of 3. So 1, 2, 3, right there. and at 0 I will get a value of 4. So this graph will go through here, go through there, and then at 2 it crosses, at -2, sorry. It will, when x is -2, it will cross through here, so this looks like that. Okay, for the second part of it, I will get this graph where I've got another parabola. This time it's opening upward, and it crosses over here up at 2, and we're going with the x squared theme. So if I put in 0, actually let's go with 1. If I put in 1, I'll get 3, but it's not equal to it, so it's kind of open and goes in that direction. All right, well, for this one, I want to know what is the limit as I approach 1 from the left. So 1 from the left would be in this direction, and if I approach 1 from the left, the limit is going to be 3. So for here, the limit as x approaches 1 from the left is going to be 3. Okay, so then let's look at the next one. So because I'm using this equation, right? From the left, here's 1. From the left, I would use that equation. If you want to do it without looking at the graph, from the right, here I'm approaching from the right. I'm going to use this equation. We're going to do the direct substitution. So over here, you could say the limit as x approaches 1 from the right of 2 plus x squared. You're going to plug it in, and you're going to get 3 as well. So the limit from the left, limit from the right, that means the limit as x approaches 1 will be 3 as well. Now let's take a look at this next one. F of x, we've got the absolute value of x minus 3 over x minus 3. Let's sketch the graph over here on the side again. And something's happening obviously at 3. That's my break point, we will call it. So at 1, 2, 3. And if I put in, say, a value of 3, well, I'll get 0, right? Or I'll get undefined, 0 over 0 in this case. So we have to take a look at this in two different ways. The absolute value of x minus 3, right here, is actually two things. It's x minus 3 if x is greater than or equal to 3, and it's 3 minus x if x is less than 3. That's just based on what the definition of absolute value would tell me. So then I really have two equations over here. I've got to deal with two different things as I'm approaching 3. So that means if I'm approaching 3 from the left, so the limit as x approaches 3 from the left is going to be this situation where I have 3 minus x over the x minus 3, and this will give me -1. Now, if you actually graph this, you'll see that this value will be at -1 right here all the way, and then on this side we're actually doing 3 at 1 right there, and it's going to go in that direction. So we could say the limit as it approaches 3 from the right, this one is the x minus 3 over x minus 3. In this case they reduce out, so it's just 1. So in this case, the limit from the left is -1. The limit from the right is +1. So that means the limit as x approaches 3 is going to be dne. It's not going to exist. So now we can get into infinite limits. And for infinite limits, we have f be a function defined at some point on an interval that contains a number a, except possibly at a itself, like we always say. And we get close to a, but not at a. Then the limit as x goes to a of f of x equals infinity means that for every positive number m, there is a positive number delta such that the absolute value of x minus a is between 0 and delta, then f of x is greater than m. Now we could do negative infinity. Let f be a function defined on some open interval that contains a number a, except at possibly at a itself. The limit as x approaches a of f of x equals negative infinity means that for every negative number n, there is a positive number delta such that the absolute value of x minus a is between 0 and delta, then f of x is less than n. So let's do this example where we are finding the g of x. We need to find the limit as x goes to 0 of g of x. Well, in this case, if you were to actually graph this, you will see that I should have done it in black here. And then you will see that this graph looks like this. Whenever we have these over x graphs, they're going to do something, and this one's x squared, so it'll look like this. They're going to do something as far as asymptote-wise, and this one looks like this. Now, here's the one thing. As you get to 0 from the left and from the right, so here's what I want you to think. I've got negative 3 over x squared. If I get 0 from the left, okay, so I'm coming in from the left side, that means I am negative 0.01, right? Negative 0.0001, getting closer and closer to 0. All right, so something over a really, really, really small number squared. So this will be negative 3 over a very small number. And if I'm even squaring that really small number, that's going to be like 1 over something huge. Well, this flips up, it multiplies out, so this equals a very big, and since it's negative, very big number. So basically think of it like this. Doesn't matter what you have on top. If you have a really, 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 really tiny number as your denominator, you're going to get a big number when you divide it. And vice versa. Okay? If you have a really huge number on the bottom, you're going to go to 0 when you divide it. Over here, if I take this from the right, it's going to give me the same situation. I'm going 0.01, 0.0001, etc. And I'm going to get a negative, very big number. When I take this over very small squared, I'll get the same thing because of that negative right there. Okay, so that's why these go in this direction. They both converge, so this limit is equal to negative infinity. And finally, we are going to do a proof. We are going to do, I'm not going to put these on the test, and you don't have this on the AP test. I will ask you to solve for delta, and I'll save those examples for class. But for right now, let's do a proof. And all of these proofs, you're going to have some in your homework. All of these proofs follow the same exact format and the same exact pattern. So watch what I do with the pattern. We need to prove that the limit as x goes to 3 of x squared is 9. Well, obviously, you can plug it in and get 9. But here's how we do this. We're going to write it all out. We're going to say, given any positive epsilon greater than 0, we can find a positive delta. We can find a positive delta greater than 0, such that you don't really have to say positive epsilon greater than 0. Obviously, it's going to be greater than 0. You don't have to say greater than 0 here, okay? So we could say, given any positive epsilon, we can find a positive delta, such that, now, all your proofs are going to start like this, okay? So what you see in red here is what they're all going to have in common. What I do in the blue color is what will be different for each problem. So here I'm going to say the absolute value of x squared minus 9 is less than epsilon whenever 0 is less than the absolute value of x minus 3, which is less than delta. Now let me explain to you where I got these values. So here's where I got the x squared minus 9. Right here. X squared minus, so just bring this over. You're looking at these two values, and you're going to say x squared minus 9. You're just going to bring it over, right? Pretend like you're solving this or putting everything on the same side. So then we're going to figure out where I got this x minus 3. Well, look at the limit. The limit as x approaches 3. So I'm going to take this, and I'm going to say x minus 3. Now here's a trick. Now, since, let's change the color, we've got x squared minus 9 equals x minus 3, x plus 3. The trick is I need to get this right here to match this somehow. I need to manipulate what I have here to match what I have there. So what I can do to this is I can factor it. Now I have partly something matching. I have the x minus 3's that match. So we can say we have right here, and I'm going to rewrite this, the absolute value of x minus 3, absolute value of x plus 3, and that's going to be less than my epsilon. Okay? So I had to get this and this to somehow match partly, and I did. I took my x squared minus 9 and I factored it. Sometimes you may just have to subtract something over. You may have to take something out. It's gonna change for each problem. In this one, it was just a matter of factoring. Okay, but now I need to get the x minus 3 by itself. So that's the goal, is to get this x minus 3 by itself. So what I can do is I can say, thus, the absolute value of x minus 3 is less than epsilon over x plus 3. Now I can drop the absolute value for this one because it's got to end up being the positive. So on this one, I can drop these absolute values right there and right there. Let me just rewrite it. In fact, I can drop them on all of them. But we're going to say, so we'll leave it right now. So choose delta to be epsilon over x plus 3. So what you have is you have set up this proof with the epsilon to find the delta. And to do that, you got to get somehow these two to match and isolate this part. Okay? So it'll always change. It'll be maybe x approaches 5. So then you have to try to find the x minus 5 and isolate that part. So I isolated the x minus 3 part, and that gave me this. The x minus 3 ended up being what I substituted in for delta. So this is what I have to choose for delta right there. Okay, so now let's finish off this proof. Now, since delta, let's put the other color, delta equals epsilon over x plus 3, it follows that 0 less than x plus 3, absolute value x minus 3 is less than epsilon, and by definition of a limit, the proof holds that the limit as x goes to 3 of x squared equals 9. So basically it's the blue. The red will be pretty much the same for every one of these proofs. You're just changing the blue. What do you find in the blue? One more time. You get this x squared minus whatever's on the side, or whatever this limit is minus whatever the value is. Okay, so up here, if we had, for example, let's go up here. If we had the limit, well, I'll just give you one. So suppose we had the limit as x goes to 5 of 2x plus 3, and well, we know that's going to be 13, right? So I would subtract this over, so I would say 2x plus 3 minus 13, right? On this side, I get x minus 5. I have to get this somehow to match that. And that's what the manipulation is in the problem, to try to get it to match it somehow. And you could do this in this problem because you have 2, right? And then x minus 10, and then you could take the 2 out, and now you've got your x minus 5. So there you go. In that problem, it would be just as simple as doing that route, like just like that. So this would give you your values that you would be substituting in right here, right here, right here, all that, just by doing this little math step. All right, that was your first real calculus proof. Luckily, we're not going to do a whole lot of them, as I mentioned. I am going to teach you in class how to solve for that delta and how to isolate that delta. But that's what I'll be quizzing you on and testing you on, and how to find the exact delta if I give you a specific problem. So thanks for watching. Make sure you hit that like and subscribe button, and I'll see you guys in the next video.